Hi everyone, I'm Xiamen from Xiamen University. It's my pleasure to present here. The title of our paper is Boosting Full Node Repair in Erasure-Coded Storage. This is a joint work with my dear co-authors from the Chinese University of Hong Kong and Tsinghua University. As we know that data volume is growing explosively, making failures rise prevalently. Thus, the fault tolerance is critical. To protect data against failures, the redundancy techniques are introduced. One is replication, which keeps multiple copies across different nodes, but easily brew up storage overhead. The other is erasure coding, which introduces slightly computational operations with lower storage overhead and preserve the same reliability guarantee as replication. Erasure coding is now deployed in Google and Facebook and etc. Erasure coding operates data as follows. It first divides the data file into k chunks and encodes them to generate another m parity chunks. It distributes the generated k plus m chunks across k plus m nodes to tolerate any m node failures. For example, for km equals 2, we can partition file into 2 chunks and encode them into 4 chunks. Once the chunk fails, we can repair the lost chunk by reading any 2 available chunks and decoding. However, erasure coding may induce substantial repair traffic, as it needs to take back k chunks to repair a failed chunk. To relieve the I/O amplification problem, there are always 2 ways. One is to design repair-efficient codes with reduced repair traffic, such as locally repairable codes and regenerating codes. They want to address the problem of what to retrieve. The other one is to propose efficient repair algorithms to parallelize the repair process, such as CC, pipe, and PPR. They want to address the problem of how to retrieve the wanted data and how to repair efficient codes reduce repair traffic. Locally repairable codes add a configuration parameter L and organize the K data chunks into L groups and generate a local parity chunk for each group. The figure shows the stripe of LRC422. Once chunk D1 failed, just retrieve other 2 chunks D2 and L1 in the same group for repair. LRCs reduce the number of retrieved chunks from K to K divided by L at the expense of additional storage costs. Repair algorithms focus on how to quickly retrieve the surviving chunks over network. The figure on the left shows the repair solution of D1 under conventional repair when K equals 4. It transmits 4 surviving chunks at the same time to the destination node N1. Because of the congestion of download link of N1, it takes 4 time slots to repair. The figure on the right shows the PPR algorithm. PPR decomposes the repair into multiple substages and executes them in parallel. Then we see how it works. In the first time slot, transmit D3 to D2 and generate an intermediate chunk I1, while at the same time sending P5 to D4 to generate intermediate chunk I2. In the second time slot, transmit I2 to I1 to restore the lost chunk D1, and in the third time slot, deliver D1 to the destination node N1. PPR completes the repair in 3 time slots. However, PPR introduced transmission dependency, as we can see that D4 should wait for P5 for aggregation. When existing attempts are directly used for full node repair, we identify the following limitations. The first limitation is failing to utilize the full duplex transmission, so cannot properly balance the upload and download repair traffic in the full node repair. Take two chunks repair under conventional repair as an example. Solution A needs to download full chunks at node N3 to complete the repair, while solution B only uploads and downloads at most two chunks for repair. It indicates that balancing the upload and download repair traffic has potential to reduce the overall repair time. The second limitation is failing to fully utilize the bandwidth at each time slot. While existing repair algorithms can accelerate single chunk repair, simply deploy them to cope with the full node repair may cause link congestion again. Let's see an example. After the transmission in the first time slot, the transmission of C3 and C7 compete for download link of M3. Solution A and B gives different priorities for them and result in different repair time. As we can see that 4 time slots for solution A and 3 time slots for solution B. It indicates that the repair solutions in the full node repair should be carefully scheduled. Our main contributions include: we propose a framework repair boost to speed up the full node repair, which builds on 3 design techniques: repair abstraction, repair traffic balancing, and transmission scheduling. We implement the prototype with C++ and integrate it into HDFS. We intend to tackle multiple node failures and boost the repair in heterogeneous environments. We evaluate performance on Amazon EC2. Let's start with repair abstraction. We formalize the single chunk repair through a repair-directed acyclic graph, which is called RDAC. RDAC describes the data routing over network and the dependencies among the requested chunks. For ISKM, the RDAC of a lost chunk can be initialized over k plus 1 vertices. See an RDAC of PPR when k equals 4. There are 4 nodes V1 to V4 to retrieve chunks, and V5 is the destination node. The age from V3 to V4 indicates that V3 is a child of V4, and V4 should collect all its children before sending data to V5. With the previous definition, let's take a look at how RDAC guides the repair process. The repair starts from the leaf vertices, like V1 and V3 in the figure. After V1 sends data to V2 and V3 sends data to V4, the edges from V1 to V2 and V3 to V4 can be removed. Therefore, V1 and V3 have no edge connecting to them and can be removed too. Similarly, as the repair process, the edges and vertices on the RDAC are iteratively removed. After constructing the RDACs for the lost chunks in a fail node, we decompose multiple RDACs into vertices and map them to storage nodes, such that retain fault tolerance degree and balance the upload and download repair traffic. The vertices of RDACs are classified into 3 types, including intermediate vertex, which download chunks from its children and upload intermediate chunk to its parent. Root vertex, which only downloads data. Leaf vertex, which only upload data. We give different priorities to carefully assign vertices to storage nodes. Take an example of how it works. We decompose the RDAC into vertices with upload and download load tuples. For example, v4 with tuple 1, 2 means v4 upload 1 chunk and downloads 2 chunks. We sort vertices by priorities. Then map each vertex to an optional storage node with the lightest load, and update traffics afforded by each storage node. We map v4 to node M5 and update the tuple of M5. Repeat the process until all vertices are mapped. Finally, we can learn the data routings among nodes. To further saturate the bandwidth utilization of each time slot, we formulate the transmission scheduling as a maximum flow problem. Suppose there are n storage nodes involved in repair. We construct the network over 2n plus 2 vertices with n senders and n receivers. M edges between senders and receivers represent the network links. We establish the connection between senders and receivers according to the RDEX and find the maximum flow over the network. Denotes the most chunks that can be transmitted simultaneously at this time slot. Take an example of repairing 2 chunks among 5 surviving nodes. In the first step, we construct the network based on edges that have no precursor dependencies into RDEX. In the second step, we find the maximum flow. In the third step, we update RDEX by removing the edges associated with the transmitted chunks and mark the leaf vertices. Then we repeat the construction of the network and the finding of the maximum flow until all the lost chunks of the failed node have been repaired. We implement repair boost as an independent middleware running atop existing storage systems to instruct the repair operations on behalf of them. The prototype comprises a coordinator and multiple agents. The coordinator manages the metadata of stripes and instructs the repair with agents. The agents are running on the storage nodes to read and write data and repair the data cooperatively. We run experiments on Amazon EC2. We allocate 17 virtual machines with 1 coordinator and 16 agents. The network bandwidth is set to 1 gigabit per second. For default configurations, we set the chunk size to 64 megabytes and the packet size to 1 megabyte. We choose IS63 as Erasure Coding. We consider following single chunk repair algorithms, including conventional repair, partial parallel repair, and repair pipelining. We select the random selection approach as baseline and mainly focus on repair throughput, which is defined as the size of data repaired per time unit. We first compare repair boosts with the baseline. When deployed for different erasure codes and repair algorithms, we can see that Butterfly 4.2 code reaches the highest repair throughput, as it needs to fetch only half of the data. In addition, repair boosts can improve the repair throughput by an average of 60.4% for different erasure codes. We also perform the breakdown analysis. We can observe that repair boost achieves 45.7% and 19.8% higher repair throughput than repair traffic balancing and transmission scheduling, respectively. We try to tackle multi-node repair. We vary the number of failed nodes from 1 to 3 and measure the repair throughput. We can see that the repair throughput of repair boost drops slightly when more nodes fails, as Fewer nodes can be selected to participate in the repair. To conclude, we propose Repair Boost, a scheduling framework that boosts the full node repair for various erasure codes and repair algorithms. We employ graph abstraction for single chunk repair. We then balance the upload and download repair traffic and schedule the transmission of chunks to saturate unoccupied bandwidth. We release our Repair Boost prototype for public use and verification. That's all. Thank you for your attention.